Hi guys, you're welcome to this session of um our close bootcamp, and today we're gonna do triple integrals. If this is the first time you are joining us, please do also subscribe. Or you've joined us over the various sessions but you haven't subscribed, please do also subscribe so that you can be part of the family and you'll get updated anytime there is a new upload. So we didn't just go straight to triple integrals. We started from the fundamentals, from domain did we did partial fractions, we did total differential, some applications, then we came to double integrals, and now here we are triple integrals. I don't think triple integral will sound something unfamiliar, because if you know double integrals to be double like this, then triple will be what? Triple integrals. Remember that when you talk about several variables, you are dealing with x, y, and x, y, z, right? So xy go for the double, xyz go for the triple. So then what are triple integrals? How do we solve them? How do we solve the different types of triple integrals, and what are the applications? That is what's going to be covered in this video. Take load to your seat. Don't move. Please watch the video to the end. Even if you miss, please do want to visit it another time so that you can grasp the full understanding of triple integrals. Good. So let's get straight to what we have. So triple integrals generally is represented as triple. See the integral sign. We use three of them, okay? Then you write your e, okay, of a function f of x, y, z, dv, where v here is your area of integration. What are you integrating over, right? So this speaks about our order of integration. E is the region, okay? You clearly understand. So remember what you call iterated integrals, right? What I gave you rectangular region, right? So I gave you something like a b cross cd, right? That was in the case of double integrals. In the case of triple integrals, it's the same scenario. But here we are dealing with three dimensions. Okay? Okay, so the first type, as usual, will be what? Rectangular region. Okay. So you do rectangular region, then you move to the general regions. Okay. So anytime you hear rectangular regions, you are trying to say that the region of our interest is made up of only, I mean, constant. Okay. So here we have a box, like a volume of a box. Okay. So the region is going to be set that a comma b cross c comma d cross e comma f, right? We are entering the third dimension. So this is for what? For x, this is for y, and this is for the respective domains, okay? The boundaries in the different directions. Okay. So let's solve some problem. Some geometry. So for the rectangular region, I think you are already used to, because we did a couple of them in the double integrals. So then let's solve an example here. Evaluate the triple integral over region E 8xyz dv where our region is equal to the boundaries is equal to 2 comma 3 cross 1 comma 2 cross 0 comma 1. Right. So this is one of the most basic problems you can ever get under triple integrals, where you have rectangular domain. Here we call it rectangular. That's why you call it box. Okay. Rectangular is more of 2D. But when I use box, we are entering the third dimension. Okay, the 3D. Okay. So now you can see that, as I said, this is for what the x, this is for what y, this is for what z. So our order here, which is the volume, is going to be, so our dv will simply be equal to what, um dx dy is a, right, good. The order may count depending on how you want to order it, right? So I mean, I think it's appropriate to go by dx dy dz, but sometimes complexity of the function counts, which you should take note of that. So here I'm going to have my outer. So since I'm going by the x dy dz, meaning dz will be my outermost integral. Okay. So what are your coordinates? 0 to 1, right? So we write 0 to 1. Then we come to y, which is the second inner. I have 1 to 2. Then my innermost, I have from 2 to 3. My function 8 xyz. Then your dv now changes towards the x dy dz. Apparently, somebody could have also made it dy, dx, dz, dz, dx, dy, whatever you want to do. It's just the v, okay? But make sure that anytime you change your dx, dy here, the order here, it should reflect at your boundaries. Otherwise, you are obviously going to get it wrong. So that's a big deal. So with this, we always tackle the innermost integral first before we moved outwards, right? So tackling the innermost, that is the dx, we have to integrate this expression with respect to x. Everything becomes a variable and it moves outside our integral. So we have 0 to 1, 1 to 2. At this point, 8 yz will move out because it's not part. It's a constant. We are integrating with respect to x. So I'll have 2 to 3, right? X, right? Dx, dy, dz. As simple as that. So at this point, what are we getting? When I integrate x, I'll get x squared on 2, right? So my 2 cancel 8 and I'll get 4. So I'm expecting from 0 to 1, from 1 to 2, I'll have 4yz x squared, right? Then just quickly I'll put my points, boundary points inside. I have 2 to 3. When I put 3, wherever I see x, I'm going to have 4yz multiplying 3 to the power 2, right? Let me make it bigger brackets, right? Minus, I'll put 2. So that will be what? 4, right? Good. I mean, you should understand this, right? Instead of me writing 4yz 3 squared minus 4yz 2 to the power 2, I made it 4yz. Then I opened my area, right? So this is 9 minus 4, that is equal to 5. So I'll simply have integral from 0 to 1, from 1 to 2, sorry. So now I know that my whole solution here is what? 5 times 4yz. That's going to give me 20yz. Okay, 20yz. So 1 to 2. So 20yz. Then become y dz. So at this point, you are left with what? 2 to conquer. With the 2 left here, you do the dy first. So I have integral from 0 to 1, right? Then for my inner integral here, which is y, I'm integrating 20y z with respect to y. So z and 20 becomes a constant. So open 20y or 20z rather out. Integral from 1 to 2 of the expression y dy dz, right? You can put this into a small bracket with your outer integral not affected. This simply gives us, this is y squared over 2. That's going to give us 10 cy squared, right? So integral from 0 to 1 being my outer boundaries. I enter, I get 10 cy squared. Then the limit is from 1 to 2 dz. I'll put 2. That's going to give me 4, right? Minus 1. That'll be 3. So that will give me 30z. Integral from 0 to 1 dz. At this point, I only have z. This gives me 15 d squared from 0 to 1. I'll have 15 minus 0, that is 15. So this is how we do a very simple triple integral over a box region. I'll use the word box because it's L times B times H, and that is it. Okay. Now let's introduce the concept of volume. Concept of volume. We can use triple integral to determine the volume of a region or an area formed by a surface. You get it? So given any surface or given any geometric shape formed within the 3D space, I can use triple integral to find the volume. I hope you remember that the application of calculus with single variable, we could find the volume which a curve makes after revolving around either x or y axis, or even revolving around a particular a particular line. Yes, so here we are moving in the 3D space, meaning that we can find the volume of the area bounded, or maybe, yes, bounded by a certain surface, created by a certain surface. As simple as that. So we say that the volume of the 3D region is given by V is given by the triple integral over a certain region E dV. As simple as that. As simple as that. Just find the triple integral over the region, then dV, where dV is any order for the x, dy, dz. Let's quickly talk about general regions. General region. I think this is a little bit technical, even for double integrals over general region. That's where it's a problem. So please pay careful attention here. At this point, I would also entreat you to subscribe if you haven't done so. Okay, do well to subscribe to support the mission so that you always get more of this. Support your journey. Now, when you talk about general regions, we are talking about a situation where your triple integral is not necessarily bounded by a box. Okay, you have curves, you have some quadratic surfaces creating the region. So therefore, we need to be tactical and we draw. There are three actually instances of this. Okay, but let's analyze the first instance. I have my 3D space here. This is my z. This is my x. This is my y. The first instance is when we have the 3D shape in parallel with our z-axis. Second is when it's in parallel with x, and when it's in parallel with y, we give us the third scenario. So there are actually three different scenarios for general region in um 3D. Okay, in 3D, something like that. Okay, so I'll have my shape. So I have my 3D shape here. I have my shape here. Good. Since it's parallel to my z, I'll have my base to give me z1, or z is equal to u1, a function of xy. Okay, you should get it. Anything which is parallel with the z within your functional domain, it takes x and y and gives out the z, which is the height. The top is going to be bounded by z equals u2, a function of xy. Then you realize that we can trace this to give a reflection in our xy domain, right? So the reflection of this gives a boundary called D, a boundary region called D. We see that this is a 3D surface. I have surface 1, I have surface 2, then I have the outer surface. I can easily get a boundary for my this surface and this surface, but the outer surface we need to project on XY. Upon projection, it becomes a surface. Okay, it becomes a surface, and this surface gives us the region D. You understand the region D very soon. So region D is simply going to be any function of XY. Therefore, we can write the region E from our integral. Remember, we said that the volume is given by what? Triple integral over region E. So our region E for this case scenario, or this case study, is given as XYZ. That is a function XYZ. Okay. So that XY is a member of D. Okay. Where we have the U1 XY being less than Z, right? Being less than or equal to u2 xy. As simple as that. So here you can see that the region of our integration here, we have the z, which is within u1 and u2. Then aside that, we have what? The area d. So it's 2, giving us the volume. So the area d and our z, apparently the height. Okay, that gives us volume. Because volume is simply equal to area times height. Okay, so the area times the height, and the height given or contributed by what? The z. If you are to do the any of the other scenarios, which if I'm to do, I'll draw something like this, right? So this time I still have my z, I still have my x, I still have my what? Y. But this time my shape is going to lie this way and lie what? This way. You realize that my area will fall at this side. My area will be created here, right? At the z domain, right? So this is where my d will be. And apparently this will be my height. So I'll have here to be x is equal to u1, a function of xy. I also have here to be x is equal to u2, a function of xy. I don't know if you get it. So here, the boundaries, we have x bounding, then its reflection to give us our d, which is the area, will be on the z side, which will change this. That we rather have what? YZ. Here, we have YZ. So here instead of X, I have what? YZ. Something like that. Right? Whilst here will be what? X. Similarly, the other one too is supposed to have what? XZ, right? Then here will be what? Y. That makes the difference for general region or the different possibilities for general region. So on that note, I think we can solve example on the general region so that you appreciate it better and you understand it so well. So let's take an example on the general region. So the problem says that evaluate integral triple e, right? 2x dv, where e is the region under the plane 2x plus 3y plus z is equal to 6. That lies in the first quadrant. In the first octant. Evaluate the triple integral of a function 2x, right? A function 2x over the region E dv, and E is defined as the region under the plane 2x plus 3y plus z is equal to 6. Okay, so what we do is we sketch, okay, and you know that for us to sketch this, find the intercept, and I have my 3D. This is a 3D space, right? So z, and I have here to be y, I have here to be x. At my intercept, I have 2. Function will be 2. At my y, I'll have 3. And at my z, I'll have what? 6. Therefore, my shape is simply going to be something like this. Okay, something like this, like this. So this is how slanted the region is. So we are interested in the region under the plane. So this is the plane we are talking about. So the region under. So let me shade the plane. So the plane, I can shade the plane this way, right? So this gives us the plane. Then the region we are looking for is actually this region, this side, okay? Because the problem stated that we should find the volume of the region under this plane that lies in the first octant. So specifically, it has restricted us to the first octant. Remember something, if I'm to project this plane on my XY plane, you know what I'll get? I'll just drag this down. So I'll end up getting a point zero zero here. This on my Y, I'll get a point what? 03, right? Then on my X, I'll get a point what? 20. I don't know if you appreciate that. Sorry. No, I think I inverted. So let me draw the XY plane. So if I project this on my XY plane or YX plane, right? So I'll have the plane lying here. So this is just you trying to reflect it on the XY plane. Okay. So when you want to reflect, as I said, on the X, where did they cut? On the X. Okay. So we had, so for us to put on the XY plane, meaning that you have to set Z to be what? Zero, right? And for us to find any of the terms, so let's see something. If you want to find the value in the, or should I say x-intercept, or if you want to find the point at x, you set yz to be 0. That's going to give us 2x is equal to what? 6, s will be what? 3. So at the x is, when you are reflecting it on the xy plane, it changes. Yeah, because it was in the 3D space, that's why we took 2, we took 3, and we took 6. Okay, but when I try to push it down and use the shadow on the xy plane, at my x, my intercept is rather going to be what? S equals what? 3, as you can see upon calculation. So you get 3 comma 0. Then my y, I'll set x 0, z 0. That will give me 3y is equal to 6. Y will be 2. So I'll have here to be what? 2 as 0 2, right? As my 0 2. Sorry. So if y is 2, x will be 0. So 0 9 6. Then originally here is also origin. So it's 0. Now you have this. You ask yourself, this line will come from our plane. If we project our plane from 3D to 2D, what it means is that we are going to make z 0. Making z 0, we'll end up getting equation of a line giving us 2x plus 3y is equal to 6. We can either make x the subject or y the subject. Remember when we were drawing general regions for double integral. So here there are two possibilities. X will be equal to what? Negative 3 over 2y plus what? 3. Or we can have y is equal to, that is making y the subject from this equation. I'm going to have negative 2 on 3x plus 3. So these are the two ways. You see how you use these two scenarios. Okay. So once we have this, we go back to the problem. What's the problem saying? Problem is saying that you should evaluate the volume or the triple integral. But they are saying that the plane is lying in the first octant. Lying in the first octant. So lying in the first octant means that we are above the origin, okay, and it's positive. Okay. So meaning that our function z, or the z, right? So here what we do is you make z the subject. Since we are in the first octant and we are in the xy plane, our reflection here, sorry, z now becomes our height. Okay. So if you remember, um so if you remember, you're going to have z from here. You make z the subject from here. Okay. So that's the first limit we can get. Remember, we need three separate limits for our x, for our y, and our z. Our z, we get the limit directly from here. Okay. So we get z, right, is equal to 6 minus 2x minus 3y. But since we are in the first octant, z is expected to be greater than 0. Okay. So we just say that z is greater than or equal to 0. This will be z, but less than or equal to 6 minus 2x minus what? 3y, because we are lying behind the plane, the region under the plane. Okay, so this is our first limit. So this is our first limit, like this. Okay, once we achieve this, the next thing is to find the boundaries for x and y. Is that not it? To find the boundaries for x and y, when you come here, as I said, for any it becomes a double integral. Okay, once you take z out, it becomes a double integral. So let me come back to the double integral. Whenever you have your region like this, there are two ways. Either you are slicing in parallel to y or slicing in parallel to x. Each will give you two separate outcomes. In slicing in parallel to y means that you cut it this way. Cutting it this way, you start from the lowest. So our y value will start from the lowest and touch the function. So our y will simply be greater than or equal to 0, but less than or equal to what? The bar, but it will be in form of a y, negative 2 over 3x plus 3, like we did for here y. And once we take our function parallel to y, our x will assume a constant value here, that is from 0 towards 3. So x will simply be greater than or equal to 0, but less than or equal to 3. Okay. Or we could have sliced through in the y-x direction. Okay. That will also give us something different. So if I had sliced through this, but it's supposed to give the same result, then it means I'm moving parallel to my x. In moving parallel to my x, you can see that I'm starting from 0, that is s equals 0, to hit here s equals negative 3 over 2y. So that will be what? X will be greater than or equal to 0, but less than or equal to negative 3 on y plus 3. And then you take our constant from the y direction. That will be from 0 to 2. So our y will be greater than or equal to 0, but less than or equal to 2. And that gives us the separate boundaries for x, y. Then we just move straight integrating, as simple as that. So let's go by the y, the first approach. It should be enough. So in our triple integral, we always make sure that the constant values become the outermost integral so that we end up getting a constant. Don't put the functions at the outside. Okay. So here you can see that our function is dz. Dz is a function. Here the y is a function. So x will go out. Okay. We have x at the outer domain. So 0 to 3. We come to the y from 0 to what? Negative 2 over 3x plus 3. Then we come to a z, 0 to 6 minus 2x minus 3y. And our function also is 2x. You come. The what? The inner one is the z, the y, the x. As simple as that. The z, the y, the x. So let's do our first integral. That's the innermost. When I integrate 2x with respect to z, I'll simply get to 2x, right? So I have 0 to 3. I have 0 to negative 2 over 3x plus 3. Then when I come here, I'll have 2x, then z, right? Where I'll have 0, 6 minus 2x minus 3y. I'll just put it inside. When I put 0, I get 0. So obviously, I need 2x multiplying the expression 6 minus 2x minus 3y. And that gives us 12x minus 4x squared minus 6xy, right? So that will be the next. So 0 to 3, 0 to negative 2 on 3x plus 3 of the function 12x minus 4x squared minus 6xy. Then we have our region, then becomes, we simply get y x. Okay, good. At this point, you're integrating with respect to y. So what am I getting? 12xy minus 4x squared y minus 6x, so no, minus 3xy squared minus 3xy squared. Then we put in 0 to negative 1 3 x plus 3. That's a lot of work. So 12x, wherever you see put negative 2 on 3x plus 3 minus 4x squared multiplying negative on 3x plus 3 minus 3x, then y squared negative 2 on 3x plus 3 all squared. That's a lot of computation, right? That's a lot of computation. So this one, let me cut things short so that we can cover more. Yeah. So I'll simply have integral from 0 to 3 of the expression 12, right, the word, that'll be hell. So we're going to have 4 over 3x cubed, right, minus 8x squared plus 12x dx. I believe you can do this simple simplification to arrive at this, okay, dx. Once you have dx, we go ahead and integrate. When I integrate x to the power cube, I'll simply have x to the power 4 divided by 4, which will give me 1 over 3 x to the power 4, right? Then here is minus 8 on 3x cubed. Then this becomes plus 6x squared from 0 to 3, right? When you put in your value, you're supposed to get the answer to be 9. So this is how we solve for general region. I believe you appreciated how the process went by. Okay, so without wasting time, let's solve a beautiful general region once again. It says that determine the volume of the region that lies beneath the plane x plus y plus z equal to 8 and E. front of the region in the y plane. That is bounded by z is equal to 3 over 2 y and z is equal to 3 on 4 y. Good. You say that determine the volume of the region that lies behind the plane x plus y plus z is equal to a, and in front of the region in the yz that is bounded by z is equal to 3 over 2 square root of y and z is equal to 3 over 4 multiplying y. How do we solve this problem? This is an application of, or is a problem under triple integrals over general region. But here you realize that we are bounded by what? Z, right? Z is equal to this and this and that, right? So please, whenever they give you this problem, the first thing is to sketch your boundary, okay? Now, given Z and Y, meaning that we are in the ZY plane. So please, this example should teach you that our reflection is this example should teach you that our reflection is on the ZY plane. So I'll have Z and I'll have Y here. Whilst my function is rather hot in parallel with my X. So this is the second or the other scenarios which we didn't I mean you should get it, of course, right? So once I have this plane, set Z is equal to 3 over 2 root Y. Please, you should learn how to sketch curves at this point. How do we sketch this curve for you to appreciate? Now, you remember from application of differentiation that if you want to sketch a curve, you need to determine the critical point. You determine whether the critical point is maximum or minimum. Then you try to draw a line to favor whether it's moving up or down. As simple as that. How do we find how do you determine if the critical point is going to be maximum or minimum? That's our point of interest. You simply have to find the second derivative. If the second derivative gives us a negative value, it means that our function is going to be maximum. If it gives us a positive, our function will be minimum. As simple as that. 3 over 2 root y. Remember that y is what? Y to the power half. Therefore, my first derivative will give me what? 3 on 4 y to the power negative half. But my second derivative will give me negative 3 on 8. That means that that part will be what? Will be something like this. But before we draw, I didn't do it. So if z is equal to 3 over 2 root y, then z is equal to 3 over 4y, then it means that 3 over 2 root y will be equal to 3 on 4y. What do I do? I simply try to cancel 3 on the both side. 2 will cancel this, I get 2. So root y will be equal to 1 over 2y. I can cross multiply and I get 2 root y is equal to y. At this point, I'll square both sides, getting 4y is equal to y squared. And I'll have y, open bracket, y minus 4 is equal to 0. Y is either 0 or hot 4. So on the y, you locate your 0, you locate your hot 4. And that gives a boundary on the y side. So once the boundary meets the x, you close it like this. Okay, yeah. Then the next thing is you have to draw the other function. What's the other function? The other function is z is equal to 3 on 4y. My first derivative is 3 on 4. My second derivative was 0. Apparently, it's going to give us what? A minimum, right? So we're going to have this like this. So this, I'll write y z is equal to 3 on 2 root y. And this z is equal to, sorry, this is going to give me z is equal to 3 over 4y. I have my boundary here and like that. And that is all. You see, we sketched it nicely, right? So the region is just lying. Now, what's the interest? Since we have reflected it the zy plane, meaning we have to make x the subject here so that we can get x as our outstanding what do we say region. Okay, so I'll have s is equal to 8 minus y minus, and since we lie behind this plane and in front of the region in the yz plane, I don't know if you appreciating this state. So what you're trying to say, lie behind, meaning we're going to have x greater than or equal to 0 and less than or equal to 8 y minus as the boundaries for x. What to be the boundaries for y? The boundaries of y is simply from 0 to plus 4. So y is greater than or equal. Finally, the boundary for z. from the smallest function to the. How did I get that? I got that by simply cutting through. So if I cut through with value of y, you realize that I'll hit this function before this. Therefore, I can say that I'll have x, no, I'll have z be greater than or equal to 3 over 4y and less than or equal to 3 over 2y. And this gives me my boundary point for my whole integration, and that is it. Okay, so you simply have to make substitution at this point. You say integral, right? Sorry, let me put the substitution, right? So let me introduce my region here. So I'll have my outermost, which is going to be the numbers, right? So y is outermost, so 0, 4, which should be the outermost. And I go inside, that will be my hot, my z. So from 3 over 2, um, so 3 over 2, y, then 3, no, 3 over 4y, 3 over 2y. Then always this one comes first. This special function, rightly directly from the function, just making it the subject, will come. So 0 to 8 minus y minus z of the function. And what's the function? The function was given as 8 minus y minus z. Okay, no, no, no. So dx. Remember the volume formula. The volume formula is saying that it's triple integral over a region E dv, as simple as that. So here we were asked that determine the volume of the region that lies behind. So here we simply put dv, and dv is obviously going to be equal to what? Our innermost, which is what? dz, dy, dx. Simple as that. At this point, what do I do? I integrate. Here there is nothing, is 1. So my first integral will be what? 1. I said 1, sorry. We are integrating with respect to z. So my first integral will be what? Z. So z and my upper and lower limit 0, 8 minus y minus z. That gives me 8 minus y minus z. So I have 0 to 4, 3 over 4y, 3 over 2 root y, 8 minus y minus z dy dx. At this point, I integrate with respect to y, and that will give me what? 8y minus y squared on 2 dy from 3 over 4y, 3 over 2 root y. When you put this inside, you are supposed to get 12y to the power 1 out of 2 minus 57 on 8y. For the sake of time, let me write it 3 out of 2y to the power 3 out of 2. Okay, then plus 33 over 32 y squared dy. Integral from 0 to 4. Rather dx. Okay, sorry, dy, yeah, dy. So, the idea is for you to understand the algorithm. Not necessarily, these are just computations. You should know how to go by the integration. These are single variable. There is no need for me to go through systematic for you to understand this. This is just an application. We are stepping up from calculus 1, go through how to integrate 8 minus y minus. No, I expect you to do that and get the right answer. So if you do this correctly, you're supposed to get 49 out of 5 as the volume behind the plane and also which lies in front of the zy plane according to the problem. So that's all for triple integral over general regions. Okay. So let's look at triple integral in cylindrical coordinates quickly. So triple integral in cylindrical coordinates. So in cylindrical coordinates, there are some problems which may demand that we convert our variables. We've done cylindrical coordinate in our earlier sessions, so you should remember. Whenever you see x, x becomes r cos theta. Whenever you see y, y becomes r sin theta. And whenever you see z, z is z. It doesn't change. Here, once you move into the cylindrical coordinate, your dv now becomes r dr. Sorry, you learn this when you are doing Jacobian, how to prove change of variables. Okay, so dv is simply equal to r z the r, the theta. Okay. So this is what you should take note of in our integral. Wherever you see the v, replace it with r, the z, the r, the theta. Please, the order counts a lot. That makes it cylindrical coordinate. Okay. Once this is done, our simple triple integral over the region E of a function x, y, z dv would then be equal to the outermost, remember, is all theta. Okay. So that will be, let's say, something like alpha and beta. Then our next will be what? R, right? So R will also be a function in terms of what? Theta. So a function h2 in terms of what? Theta. Then Z will be the inner, right? So Z will simply be a function U of x and y, but our x becomes R cos theta sine what? Theta. Let me make it theta 1. I have my U2 to be R cos theta, R sine theta 2. Please don't mind what I'm doing. So I think this is going to be a long thing. Let's solve an example, please. So I'm just showing you how to write it. So even once I'm done here, then you know a function of x, y, z. Here, you place x is for r cos theta, y of r sine theta, then my z is z. It doesn't change. Okay. Then my dv comes, which is what? R d theta. Then once you write this, you are done with your integral. Move on straight away. So meaning with here, I can write my first example, and my first example is gonna be what? Evaluate the triple integral over region E y dv, where E is the region that lies below the plane d is equal to x plus 2 above the xy plane and between the cylinders x squared plus y squared plus 1 and x squared plus y squared is equal to 1 and x squared plus y squared is equal to 4. So remember from quadratic surfaces that a cylinder is represented as x squared plus y squared is equal to r squared, right? The step is a form of what do we say? Okay, I'll say sphere, right? When you don't have z, you have z squared becomes a sphere. Okay. So now let's see the problem. It says evaluate the triple integral e y dv, where E is the region that lies below the plane. So it lies below this, above the xy plane, and between the cylinders x squared plus y squared is equal to 1 and x squared plus y squared is equal to 4. How do we approach this problem? So simply let's solve this problem. Now we're going to use cylindrical coordinates. Using cylindrical coordinates, our cylinders becomes, x squared plus y squared is equal to what? R squared. Therefore, for this cylinder, my r is 1. For this cylinder, my r is 2. Therefore, my r lies greater than 1, greater than or equal to 2. Period. We are done. The next term we are looking for is what? Our theta, then our z. Please, whenever you have a cylinder, okay, you have a cylinder problem, you realize that when you overlap the cylinder on the xy plane, it becomes a circle. A circle will have a theta from 0 to what? 2 pi. So 0 theta less than or equal to 2 pi. We are done. Once it's a circle, we are done. Then the next one is what? Z, right? We need Z. What will be Z? What will be the boundaries for Z? So the boundaries for Z is going to stem from the plane, and the plane given was what? We want the boundary for Z, right? So to find the boundaries for Z, as I said, we use the plane. Since we are lying above the plane, is it we lie what? Sorry, below the plane, yeah, below the plane. So below the plane means that our Z will be greater than equal to 0 but less than or equal to x plus 2. Once you have this, you are done with the problem because you need the boundaries to solve. That is all. So with this, we simply go straight. So our outermost is always the theta, 0 to 2 pi, followed by our r, which will be 0 to what? Sorry, 1 to 2. Then the innermost is our z, right? Is our z, which is 0. So please, our x plus 2 will change. When you are doing triple integral in cylindrical coordinate, x becomes what? R cos theta, okay, then plus 2. Then our function was what? Y, integral y. And you know y is what? R sine theta. So you have R sine theta, right? Then remember, the dv will be what? R dr d theta. R dr d theta. So R dr d. Oh no, let me go back. It's what? R dz dr d theta. R dz R dz r d. Good. So our first integral, for us to simplify the first integral, so we can multiply. So this becomes r squared sine theta, right? R squared sine theta for the y, okay, for the y. Then this y was r sine theta, right? So now when I integrate, my first integral is with respect to z, with respect to z. So when I integrate with respect to z, I will simply bring what z, and I will introduce my what 0 to r cos theta plus 2. Wherever I see z, I'll put this. My function becomes r squared sine theta, multiplying the expression r cos theta plus 2, right? And I'll have my what? D r d theta, where I'll have from 1 to 2, from 0 to 2 pi. Now, this is where you apply your trick very well. Remember, when I multiply, I get r cubed sine theta cos theta, right? Plus 2r squared sine theta, right? Here, please change it to sine 2 theta. So you have 1 out of 2 r cubed sine 2 theta, okay, plus 2r squared sine theta. So that when I integrate with respect to r, this becomes what? R to the power 4 divided by 2, right? So that's going to give us what? 1 out of 8 r to the power 4 sine of the expression 2 theta plus this one will give me what? R cubed. So 2 out of 3 r cubed sine theta. Then I also put in from 1 to 2. When I put in from 1 to 2, I'm supposed to get what? When I put 1 here, 1 out of 8, right? Then that's 2 will give me 16 over 8. That will be 2, right? So simplifying, you should get 0 to 2 pi. That will be the last integral. 15 out of 8 sine 2 pi or 2 theta plus 14 out of 3 sine theta. theta. So this is the last integral. And when you do the last integral correctly and you put in 0 to 2 pi, you are supposed to get what? 0 as your answer. So I think I've exposed you to integral in the um, cylindrical coordinate, right? So let's do the final part of triple integral, which is triple integral in spherical coordinate. Spherical coordinate. So in spherical coordinates, remember the parameters we need. We need some strong three parameters. One is what? Rho. The other is what? Theta, and the other is what? Phi. If you don't remember, let me remind you so quickly. And please check the video on that so that I remember in the session. That was our first session. So you have X here, you have your Z here, then you have your what? Y here. Please check. You have your rho. Rho is the spatial radius. It makes an angle phi with the Z axis. When I trace my spatial radius, it will reflect in my XY plane. And then in the XY plane, I'll trace and I'll have my 90 here. This becomes my theta. And this is what? My R. That is all. At this point, we can draw a Z XY plane. So here becomes Z, becomes my XY plane. Therefore, this becomes my R. My rho is here. This becomes my phi. Then this becomes my theta, right? So from here, we derive that this is Z. Okay, we derive that rho is equal to R squared plus Z squared. Obviously, we know that R squared is what? S squared plus Y squared. Therefore, plus Z squared will be what? Rho. So these are some things you should remember. Look, using this same example, right? You realize that now we are going to use, so check, this is Z. This is phi. Using this, you have phi to be here, right? Now you can say that rho, looking at this, look at this way, right? You say that rho, when you take cos 5 will be what? Z over what? Rho. So rho is simply Z is equal to what? Rho cos phi. Put it down. Z is equal to rho cos phi. Then you also know that your x will be equal to what? Um, R, right? So our x, now you have R. So r is simply equal to what? Rho sine phi, right? Rho sine phi. And you know definitely that if I have r and I want to find x, x is equal to r cos what? Theta. Therefore, replacing this, I'll have x to be equal to rho sine phi cos theta. My y is going to be what? Rho sine phi sine theta. That. So that is how we change variables from the Cartesian coordinate to spherical to cylindrical. It should be static, right? It's not difficult. So for you to appreciate this, please, all the time, I have stated all this in the I think I have to let you to go and watch that video for you to understand not so many things in this video. So, for the sake of clarity, phi is the special angle. See, this phi makes what we call the revolution. So if I have phi of any angle and I root special radius, I will end up getting the shape phi. So if your phi is 180, you end up getting a phi can never exceed 180. Okay, when it is 90, you end up getting a semi. Check it. You get a semi times 45. You get a cone. So please take note of phi. That phi is always greater than or equal to or less than or equal to pi. Our theta, the maximum is 0 to 2 pi, but it depends. It varies. So you can say that alpha greater than or equal to beta greater than alpha. Then finally, our rho. Our rho is also going to be greater than any less than any right? So it's unknowns now. So we're not talking plenty. Let's do a simple problem here. So evaluate triple integral e 16z dv. Now let's define the e. E is the upper half of the sphere x squared plus y squared plus z squared is equal to 1. Okay, look at the problem. So can you tell me that you can use the normal approach of triple integral? You can't do that, right? So that's why the spherical coordinate comes. Sorry, this called. So spherical coordinate helps to ease some of the regions which we cannot integrate over. Okay, so that means that what are you going to get? So here, when I write my function, please, you are supposed to derive boundaries for phi, then for rho, but I didn't add there. So when you are doing spherical coordinate, your dv is giving us this one is something you have to keep in mind. It's fixed. Okay, you have to understand. So it is giving us rho squared sine phi rho d theta phi. So always phi is at the outermost integral. Theta is the middle, our rho the innermost. Then you have this term rho squared sine phi, and it's always at. So let's find the boundaries. So with the boundaries, I need a boundary for rho and then the upper half of it. Let's try to visualize it. The upper half of it, I have something. Um, oh sorry, I'm having some upper half of it. That means that our rule, which is special radius, just draw a radius to hit this like this, or this revolved to, then the rule will simply be what we want. You know that the complete pi will give us full sphere. So half going to give us what pi on 2. See that our phi will be greater than or equal to 0, but less than or equal to pi on 2 fixed. Once you have a sphere, it will fall on the xy plane circle. Our theta will surely be greater than 0, but less than or equal to 2. Aside that, we need rho. How do we get rho? In our derivation for rho, realize that x squared plus y squared plus z squared is rho squared is equal to 1. Rho is simply going to be what? See, we are dealing with positive side. So let's check something here. The problem says that we are dealing with the upper half of a sphere. Please, rho is not going to be like you can't say negative. So lie from 0 to 1 because we need a semicircle. So therefore, rho greater than or equal to 0, but less than. Now we are done because we have our limit point. Right, that is it. So our triple integral will have the outermost integral to be for the phi. So from 0 to pi on 2, coming inside to theta, 0 to 2 pi, coming inside from 0 to 1. Then our function will come. What's our function? 16z. 16, right? So you replace z with what? Phi cos theta. You should know that. Z is what? Phi cos theta. Phi, right? So it is what? 16 phi cos theta. Phi cos. Oh no, rho cos phi rather. Rho cos phi, sorry. This thing rho cos phi. It's representing z. When you convert z to the spherical coordinate. Then what are we left? dv. Then the dv will follow. dv is what? Rho squared sine phi rho theta phi. So meaning that once we have this, our first simplification will be with what? With what? Rho. So what is rho? When I integrate rho, but you have to simplify this expression. So this is a little bit okay, actually hard. So whenever you are doing integrals at this level, you have to open your eyes so that you don't get the trick wrong because the trick can also be tricky. Aha. Yeah, so once you get that done, you're gonna have God. So remember that when I simplify, I have rho. So I have rho cube, I have cosine, I have sine, right? I'm gonna have cos sine. I can replace it for sine 2 theta. By replacing it with sine 2 theta, I'll introduce a half. That will make this 8 rho cube sine 2 phi. Please take note of that. Then it will come what? Rho theta phi. This expression, I'm going to integrate this with respect to rho. That will give me what? Rho to the power 4 over 4. So I'll get rho to the power 4, 2 rho to the power 4 sine 2 phi. I will replace it with 1. As simple as that. When I put 1 inside, I get what? 2. When I put 0, everything will be 0. So I simply have what? 2 sine what? 2 phi. The theta phi. Then you introduce your so the theta is 0 to 2 pi, right? Then our phi is 0. At this point, you're integrating with respect to theta. There is nothing like theta here. So it will introduce a theta. So I have 2 sine what? Pi theta from 0 towards 2 pi. And I put 2 pi in, I get 4 pi sine pi. Then from 0 to pi on 2 pi. Simple as that. When you solve this, you are simply going to have what? Negative 2 pi cosine 2 pi, right? Then you put 0 to pi on 2 inside, and our answer was 4 pi. So this is how we compute triple integral in spherical coordinate. I have shown you how to compute cylindrical coordinate. The only thing you need is your boundaries and your dv. That is all. The same algorithm. So thank you for being with me in this session. And at this point, if you still haven't subscribed, please you can't be so mean like that. You can help and support the mission by doing the best possible to press the subscribe button. Buttons get notified anytime we upload a new video. So until then, have a good day. Bye.